Alrighty, everybody, welcome back to my channel. If you're a new subscriber, I appreciate you for subscribing. I hope you enjoyed this video. If you're a returning subscriber, returning viewer, thanks for rocking with me, one of my A1 since day ones. Let's get it going. Alright, so today we have a pretty interesting challenge from crackmes.one yet again, and this one is by someone I've actually had a few conversations with. He seems like a pretty good guy to me. And this was an interesting challenge, and I enjoyed it. And so first, we're going to get started by we have our little notes.txt file as we usually do. And I'm also going to create our sudo.c file so we can write our little pseudo code that we're going to be doing later on. And this is Z CrackMe. And so I don't have it actually pulled up the website here, but I remember the goal for this one is to define the serial. And there are some rules that he set for us, and he said we can't patch, and we also can't brute force the key for the serial. So those are our only two constraints. So let's go ahead and get started here. And we always usually start off here with running the file command on there. And so we see something that's pretty interesting already, and right over here, right? So it says there's no section header. And very briefly about ELF file formats, there are section headers, like there's the .text, there's .bss, .data, .row data, and there's a lot of other section headers as well. Those are kind of the main four that we're mainly concerned with. And basically all this is saying is that it can't find those. I'm not really sure why, but that's okay. We don't really need it right now. We can still do some other analysis on this first, so we can run strings on here, and we can still figure out some things here. So right away we see this right here, that this file is packed with the UPX executable. And so UPX is a packer that compresses a binary file. Usually when I've done it in the past, it doesn't actually mangle it too much. So like if I were to try to run this right now, it seg faults. So usually when I've used the UPX packer, it doesn't do this. So I'm not sure what he did to get it to do this behavior, but that's okay. Since we know that he used the UPX packer, we can simply tell it to unpack it or decompress it, and we're going to give it an output file called unpacked Z, and you see that it works just fine. So if we run file on the unpacked version, and now it looks more like what we usually are dealing with, right? We also see that it's not stripped again, so everything looks good there. So let's go ahead and look at the symbols here, and right away there's a lot of symbols. There's a lot to kind of unpack. And so going with our goal, you see that there's a check serial, so that this function may be of interest. There's compare, which maybe it just uses to compare what we type in versus to the actual serial. There's crypt serial, so this is also maybe a function of interest that we want to analyze when we actually get into looking at this in IDA Pro. Let's see if we can find anything else in here. Gauss eliminate, that sounds insane. I'm just gonna say right now, I don't know what that function would be doing. I hope hopefully it's nothing too crazy there. Generic fizz buzz. I also don't know what that is either. Let's see. We got the main function, of course, obfuscation. So maybe he's trying to do some obfuscation to hinder us from doing our analysis. So ptrace right here, this is interesting. And so this tells us, or at least this tells me, that he may be doing some anti-debugging things. So I'm just gonna say ptrace, yep, and then maybe anti-debugging. And so ptrace is a function that you can call it in your program, and you can use it as a check to see if someone's debugging, and you can actually quit if not. So if they are, so that may be what he's doing, but we're not sure yet. And let's see, quick sort, and then there's rot. Don't know what that's doing. Swap row, to lower. There's a lot of different functions in here that may be interesting. Sorry, I didn't write down quick sort. So I think we're gonna, when we actually get this in IDA, we may want to start off with these check zeros, crypt zeros, just to see what they're doing, and then go from there. All right, so let's go ahead and run strings on the unpacked executable and see what else we can find out here. And so right away we find that we find our success message, which is you succeed, double exclamations. And our failed is simply try again. And you see right here that they are actually doing some anti-debugging, so I'm just gonna change this to yes, they are doing that. And also another thing too, there it looks like they're checking to see whether or not we are using a VM. It's pretty interesting. So checks if run in a VMware to be specific. Actually, it says VMware, so VMware to be specific. And then it prints out the rules. Let's see what else is up here. There's fizz and there's buzz. That's interesting. And here we have all the letters from A to Z, capital and lowercase, some random kind of message. And so let's see. This is a top secret text message. So this may be pretty interesting. So that may be, it could be the actual thing, actual serial. Who knows? Top secret text message. And let's see what else is in here. Alright, that's about it. And so I'm just gonna try, let's actually just try and run this. And alright, so that looks like how we expect it to be. Let's just try this out. This is a top secret text message. So this most likely won't work, but you have to try everything, and yep, it's not that easy. So that's okay. That's definitely okay. So we're gonna go over to our sudo C file. And let's go ahead and open up IDA Pro. All right, and so we already have like an idea of some functions that we want to look at first. So let's go ahead and go there, and there's the functions windows on the left-hand side here. So we can just sort of skip to the function that we want to look at first. And so let's start with, I guess, crypt serial, maybe a good one to start with. And so it looks like there's a lot going on, but before I waste any of our time right here, so this is one of those things that he really tried to trip us up and try to put us down a rabbit hole. So that, and this is actually a really smart way to do it, because he implemented this function, and so that there's actually instructions in here. But as you can see up here, usually we're expecting to see some sort of cross-reference, right? So like some evidence that this function is called, and it's not. So that means we probably don't have to worry about this function, because if main never calls this, if no other function ever calls this function, then we ain't gotta worry about it. And because we don't gotta worry about it, I ain't about to analyze it. So I'm not about to waste our time looking at this nonsense, because you know it doesn't really matter at this point, right? So check serial, let's look at that. Double click. Same thing here. So he's intentionally trying to throw us off. So, and that's something you have to kind of look out for when you're reverse engineering. Before you start just digging in, try to analyze and try to just look and see are there any cross references. If there's not, then you know you can just keep moving. So what I'm gonna do here, I'm just gonna go to the main function, because we know the main function is called, and I'm just gonna go through and run through it, and you know we're just gonna analyze it and just gonna see what happens. So let's go ahead and get started here. So this here is our argc. That's what EDI usually holds, and the RSI holds our argv here. And so this here is a way that the you can check if there's like a buffer overflow or stack smashing attack. And so they store some variable on the stack, right? That holds a specific value in there. And if it's different at the end of the program, then it'll say stack smashing detected, and it'll just quit. And so if you go down to the end here, let's see, you see that this function is called there. So that means if I were to try to do something like this, I'm just gonna give it a whole bunch of A's here. Okay, sorry. No. All right, so I think that should be enough there. And you see stacks matching detected, and we can't succeed. So we're not supposed to, he's checking for stacks matching, so that's probably not the way to go. That's okay. We can do some more analysis and actually see what we're supposed to do here. All right, and so then you see we're printing out the rules, and then the constraints there, and then this here is pretty interesting, because what I think he did, and I'm almost certain he did something like this. I don't know this is exactly what he did, but he did something like this. So you can have like you can define like a long message. You can give it, let's see, of size 1, 2, 3, 4, 5, 6, like that. And you can say do something like message sub 0 equals to, oops, not that, equals to 0 hex, right? And then what you can do here is like, so if I do this for all of these, right? So if I message sub 1, like that, there's message sub 2, message sub 3, message sub 4. Oh yeah, that's not right. 1, 2, 3, 4. Yeah, we already have that one. Sorry, should be this. And then finally, just assign 0 to the last one. So 5 equals 0. Oops. And so you can do this here, and what's interesting is that this will be interpreted as a string if you were to like print it out, because these are hex values, but they map to actual ASCII strings. And so what these map to actually is this is a super top secret message, and there's an exclamation point at the end. And so if I were to again kind of copy these values here, but you have to do it in reverse order, because we're doing this in loaded endings. You gotta start from the bottom. Started from the bottom. Now we get. Sorry. Okay. I'm sorry. Y'all know I'll be acting crazy sometimes. But all right, Anyway, so we go ahead and copy these values just like this, and we can use Python to show us the actual final value. So if I go back here, type Python, and I create a byte array from hex, and then I give it this thing here, and I reverse it because we're in little endian, so we have to reverse it and do that. And you see that we get this is the message right here. So I guess I could just try the same thing, but just put this in there. But I'm pretty sure this won't work either. But like I said, try everything, and yep, it doesn't work just like as we expected. But that's fine. Let's go ahead and let's see what it's doing with this message here. And so that's why I believe that's what he's doing, and I believe that because these are kind of evenly spaced, as you can see, they're 8 bytes apart, and an array usually holds things in memory in like about 8 bytes apart. So that's why I believe that they're probably doing this is like some sort of an array here, starting from here. And so I'm just gonna rename this to super secret message, and I don't know how to like relate this to like make IDA-Pro to say like this is actually one variable. So if you know how to do that, please let me know in the comments, because I don't really know how to do that in IDA-Pro. But anyways, this here is just one single array, but as you'll see that only this variable, this is going to be used anyway. So when you try to reference the super secret array, it'll always be used, like this will always be used in there. So then we scroll down, and this here is an interesting instruction here. So this stands for store interrupt descriptor table, if I can remember correctly. And this is one of those ways you can check for if a VM is running or not. And so I'm just gonna go ahead and say VM check here. But if you notice that I'm running this in VMware, but it's not telling me that it's not giving me an error. And I think the reason why it's not giving me error because he offsets this by 5. I don't know if he did that on purpose or not, but yeah, I'm not sure if he did that on purpose or not. But this actually doesn't work. So if he didn't put this +5 in there, I'm pretty sure that would make this check work. But I'm glad he didn't, because that means I'd have to do some other crazy stuff to get around this check, but I don't have to. So thank you, Zed, for not for doing that. Anyway, so if it's not running on a VM, we jump down here, and then we see that we load up super secret message into the RSI register eventually, and then hex D into the EDI, and then we call rotd, or just rot. And so essentially we do this: D super secret message. So let's see what it's doing in super secret message, or sorry, in rotd. Let's see what it's doing too. So it's obviously going to encrypt it a little bit. That's why we probably were getting the right value, because it's encrypting it. So EDI is our first argument. So this is going to be is 0 hex D there, and RSI is going to be our super secret message. Then here again we have our stack check. And then let's see, we grab the length of super secret message and store it into a variable. So this is going to be, I'm just going to say SSM len for super secret message. That's a little bit too long to write all the time. So SSM len equals strlen and of super secret message. Feel like we're like spies or something, you know. Sounds really cool. Super secret message. Sorry. And then so you see that we can store our lowercase letters. I'm just going to call it lowercase letters from A to Z, and then we do it for the uppercase letters. So uppercase letters. Uppercase letters. So essentially it's just lowercase letters equals A through Z, and then uppercase letters equals A through Z. Should be S at the end. There's a D on the end. And then let's see, we store 0 into bar 38, and I'm pretty sure this is going to be used as some sort of loop control variable just to check to be sure. Yep, that's what it looks like. We add 1, we compare it to that. So yep, so let's go ahead and rename this guy here to I. So we got I equals 0 while I is less than SSM len. We're going to do some things here. Let's see what those things are, shall we? Alright, so this is actually pretty interesting here. And there's a really good article linked in the description that kind of goes into detail about what this is doing. But all this is really doing is checking, first he checks if it's an alphabetic character, right? And so, like I said, the article goes into more detail about it, but basically it C type _B is like some sort of enumeration table, and we get the actual letter that we're trying to determine whether or not it's an alphabetic character or not, and then we do some checks, and then eventually we'll check to see if it's if this kind of holds, and then if it does, then we know that it's an alphabetic character, or it's not an alphabetic character, and if it's not, then we essentially skip it. So first thing we do here is we got if I guess is alpha, and then we have SSM sub I. Let's see, right, so if it is alphabetic character, then this won't be true, and we'll kind of go into this part here. And so the next part here is essentially the same thing, but now we're checking if it's, I think, an uppercase character. I can't recall exactly, but essentially he checks if it's either uppercase or lowercase, and whether or not it's uppercase, he'll do one thing. If it's lowercase, he'll do another thing. So I'm just going to say if is upper, and we take SSM sub I like this. We're going to do stuff, and then else we're going to do other stuff. And actually, we're going to find out that whether or not it's uppercase or lowercase, they're going to be almost identical. The only difference is, well, there's one small difference, and I'll point that out when we get there. But they're almost identical. And so let's go ahead and assume that it's uppercase here. So if it's uppercase here, we're going to just jump right here. And so you see that we load up RBX with the uppercase letters. So going to RBX equals to, what is this? Oh, uppercase letters. Oh man, if I can spell, right? Letters. And then let's see what we do next. Where am I at? Okay. So then we grab super secret message and we store that into RAX, and then this here is like a somewhat of a different syntax of getting the ith index of a string. So this here, so we store I into REAX, we put that back into EDX, and then so we just add RAX to RDX. It's RAX to RDX is essentially going to pick our SSM sub I, and then we get the actual value stored there. So like the actual hex value, we store that into EAX, right? So we have, let's see, EAX, and then we call it to lower. So essentially it's to lower, like that, of the SSM sub I. And then the result is actually stored in RAX. So, but I'm just gonna say like num equals this because it's gonna return an integer. So num equals to lower of SSM sub I. And then let's see. So then you see here we subtract the number or hex 61 from the number. So we store that to EDX. So EDX equals num minus hex 61, and then you see that we store EAX is equal to hex D right here. And then you see here, so now you know that RDX holds num minus hex 61, RAX holds hex D, and so ECX now, so this is saying add both of these together equals RDX plus RAX. And so if we were to substitute this value into here, we essentially have num minus 0 hex 61 plus RAX, which is hex D. All right. So this is where I got tripped up for a long time. So this here, and again, there's a better description of this there's a better explanation in the description box below. But basically, if you know TLDR, right? All this is doing is saying take ECX and mod it by and do the modulus of hex 1A. So it's because it wants to keep things between 0 and 26 or 25 maybe, yeah, 25. And it does that because it's trying to keep things within the range of alphabetical characters, right? And there's only 26 letters in the alphabet, so it has to mod it by hex 26. And so, and the reason why you would expect there'd be some divisions going on because it's a modulus, but as I was reading, division is actually a more expensive operation, so it tries to not do division if it can avoid it. And so it uses this very specific number in these series of multiplications and shifts to essentially do a modulus. And at the end here, you see that this is what we're trying to mod here, so hex 1A. So essentially we have ECX mod equals 0 hex 1A, just like that. All right, and so let's see what happens next. We store that into, where is it? We store that into EAX, so EAX equals this. All right, and so essentially this is, so what this boils down to is num minus 0 hex 61 plus 0 hex D mod 0 hex 1A. I know it's a lot, but that's essentially what's going on there. All right, and so then let's see, we scroll down a little bit here, and we see that here. So this is we're gonna choose this is that similar kind of syntax, right? So rex holds this craziness here, right? So essentially, and then we have rbx there, and rbx is the uppercase letters. So what that looks like here is uppercase letters sub num minus hex 61 plus hex d mod 0 hex 1a. Disgusting, I know, but that's what's going on. Like I know it's a lot, like all this nonsense just for this, but like, you know, that's the beauty of it too. That's the beauty of it. And so then you see, again, we're getting super secret message sub I. We store that into RDX, and then RDX plus RCX, which is I here, and then we store the actual value into EAX, right? So this is the uppercase letters sub all this nonsense, and then you see here we're going to set the value of EAX, which holds, remember this nonsense here, into RDX, which is our array, our super secret message array. So all this is to say that all this here is doing, all this nonsense right here, that whole chunk of assembly code line, it translates to these two lines of assembly right here. Num equals to lower, and I don't know if it's actually num, but I'm just giving it a number just because it's easier to kind of keep track of. And then we have SSM sub I equals to uppercase letters sub num minus hex 61 plus hex d mod 0 hex 1a, just like that, and that's it. And so he's essentially trying to mangle the letters around, and that's all there is to that. I'm going to get rid of this as well. And then so now let's look at what happens if it's a lowercase. Let's see, where's it at? Chip here. So lowercase, it does actually the exact same thing, except it uses lowercase letters. So we have num equals to lower of SSM sub I, and SSM sub I equals lowercase letters sub num minus hex 61 plus hex d mod 0 hex 1a. So the exact same thing, except now we're going to use the lowercase letters as our kind of lookup table essentially. And that's all this function is doing. You see, then it'll just continue. And actually, let me go ahead here and scroll down. So just I plus plus. And so that's it. And so we can calculate that. But if I'm going to go back to the main function here, and this is kind of where it gets a little bit annoying here, because he actually threw us down a little rabbit hole right now. So you see that we essentially encrypted with this right here, right? So this is going to encrypt this is a super secret message with the exclamation mark text, and it's going to mangle it up and change it to something else. Then he goes and he pretty much decrypts it because he uses the exact same parameters, right? We have our encrypted super secret message, and then we have the key, and since all it's doing is really just doing this lookup here, you know, when we do this when we run this function with the encrypted within the same key, it essentially decrypts the message. And so at the end of the day, we're just left with the same message. And so, like I said, he kind of threw us down a rabbit hole. He got us there. Sorry, it's, you know, but hey, let's go ahead and keep it moving. Let's see what else he's doing. All right. So the next thing here is we see a similar thing. We have this long string of hex characters here. And so I'm going to go ahead and do the same thing. Start from the bottom. Now we hit. All right. Now let me stop. And then we do this and do that. And if I copy this here, I'm going to Python again. VA equals to byte array from hex. And so actually this looks like those characters we saw earlier. I think we saw something like this earlier, so that's pretty interesting. So I'll just copy this. Alright, let's see what he's doing with this. So maybe this is the string that he's actually encrypting, and this is one we have to analyze here. So this here, I'm going to call this, let's see, maybe enc. I guess enc message is what I called it at some point in time. And we get here, you see this is our user input here, S2. So this is, yeah, user input here. Alright, and then let's see this. So this is the call to ptrace here. So he actually doesn't check it for debugging until this point here. So that's pretty interesting. So I guess this is where he wants to really say he's trying to hinder us from doing some dynamic analysis. So I think we're in the right place here, because now he's starting to get a little more strict with what he's allowing here. And so yeah, see if it's being debugged, and it'll just exit. But if not, then we take our encrypted message, we XOR it by 2. And we store that into some other string here. So I'm going to call this like the decrypted message here. So essentially what this looks like here is we have our decrypted message sub 0 equals to enc message sub 0 XOR 2. And then similarly here he does similar things. So he encrypted message sub 3. So we have dec message sub 1 enc message sub 3, and what does he do? He subtracts 10 minus xa, and then let's see, we have, what's the next one? Encrypted message sub 2, enc message sub 2. What does he do with this one? He adds xc, which is, I think that's 12. Dec message sub 3, enc message sub 2, and I think he doesn't do anything with the second time. Yeah, so he just leaves it alone this time. And finally, dec message sub 4 equals enc message, I think this is sub 1. Yep, and then he just adds 1 to it, so plus 1. All right, and so then you see here he puts 5 into this variable here. So this is going to be another loop control variable. We're just going to call this j. And we jump here. We check if it's less than or equal to hex 12. So we have while j is less than or equal to hex 12. Then we're going to do some things. And let's see here. So you move j into an encrypted message. So we encrypt the message sub j, subtract 1 from that, and then we essentially sign it to decrypt the message. So all he's doing here, so he looks like he kind of pity does and say, okay, I tortured you guys enough, let me just do something kind of simple. So I appreciate that, Zed. So he does enc message sub j. Oh, sorry, and notice he did start off with j equals 5. So we're not starting out at the beginning, because we already did some things there. So we started off at essentially the next array, which would be dec message sub 5. So dec message sub j equals to enc message sub j and -1 j++, and that's all he's doing. And then you'll see down here he takes our user input, our dec message, and compares it to user input dec message. I'll just say succeed else failed, and that's it. And so now I believe this should be the correct thing that we have to do, and actually it actually is, because it's, we have our use succeed message or our try again message. So all we have to do is decrypt this thing here. So I actually already did this. I have like a Python script that I already wrote, and I know I usually kind of write these live, but I figured that maybe you guys will enjoy just having the thing already written instead of seeing me struggle, because you guys know I be writing some nonsense sometimes. So I figured this would be an easier way to do it, just show you guys what I did and then just do it. But if you want me to actually write this script and talk about it as I'm doing it, let me know in the comments, and I'll do that in the next videos to come. Anyways, so I defined the encrypted serial as a byte array, and I used those same hex characters that I did earlier, right? And as you can notice, it's the same. I started from the beginning. It's kind of hard to see because it's 34 right there, but it starts from right here. And so I started from the bottom and I worked my way up. So it you know, because remember it's a little Indian. Then I reversed them, and then I call the decrypt serial with our encrypted message, and then essentially I just sort of, you know, do the exact same things, right? XOR it, -10, +12, all that good stuff, and then just do a while loop here. And so when I run this, I should get the actual thing. And so this is our serial here. And if I run this, we got it. And so that's pretty easy. And so before I actually wrap up here, I forgot to mention that even though he is doing some anti-debugging things, there is a way to get around that without actually patching it. So let me show you really quickly. / here. And I'm going to break at the main function. I'm going to say run. All right, just simple main. And so this is where we want to break here. So I'm going to set a breakpoint right here. And then I'm also going to set a breakpoint right here. And I'm just going to say continue. And I'm just going to give it a passphrase. And you see here, it's going to call this, and what's going to happen is it's going to get set to -1. So if I do that, you see it's set to -1 because I'm running it in a debugger. So when it does this test, it says that it's not going to take this jump. If the test succeeded, meaning I'm not running the debugger, it would actually take this jump. But it doesn't succeed, and so then it loads, you know, loads the message, calls puts, and then I'm just gonna continue. Oop, let's see, where is it at? There it is. The process is being debugged. So, like I said, there's a way we can get around this though. So let's go ahead and run this again. Continue, pass, and then let's see, hit next. And now, if you recall in one of my previous videos, you can actually set registers in here. So I'm going to set this to 0, and then I'm going to hit continue. And you see now we've gotten past it. Now we're at the place where we can see the string comparison. And you already can see here that we see that this is the password here. So we can just stop here, or what we can do is just set RDI equals to our password, and do that, and you see that we succeeded. But also, of course, then we can just take that and do the same thing. So kind of two ways you could have done this. So that's pretty much it. And so I guess to wrap up, when we first initially got this binary, we saw that there was no section headers, and then so that means we couldn't do our normal analysis, so we ran strings on here, and we found that it was packed with a UPX executable. So we just simply unpacked it with this command here, -o this, and then we got our unpacked executable. We're gonna file on that, and it's looked a little bit more normal. Then we found that there was a lot of functions in here, but we learned that these functions are pretty much rabbit holes, and he wanted us to go down those rabbit holes, but we didn't. We're smarter than that because we are good reverse engineers, right? Yeah, whatever. Okay. And so we did that, and eventually we learned that he did send us down another rabbit hole. He was successful with that, with this rot function here. But then we learned that, okay, this is the message that we have to try to decrypt or encrypt. And we used a simple Python script to get the actual message that he wanted us to do, the actual serial message. And we verified that it works. And then we just simply copied and pasted. And we got it. And then of course I just showed you that we can do all this stuff without, patching. So this is longer than I wanted to be, and I apologize, but I hope you learned some new things. If you did, give me a like. I really appreciate it. If you enjoyed this video, also give me a like. If you have any questions that maybe I kind of didn't address or I glossed over, go ahead and ask that in the comment section below. All your questions are welcome. I'd be happy to answer them. If you like this video and you want to see more of this type of content, don't forget to subscribe if you're not already. Hit the bell icon so you're notified when new videos go live. See you guys in the next one. Peace out.